Welcome to Unit 4. In this lecture video, we'll be going over a handful of properties of exponents. We'll start with the product rule. The product rule states that for any base x, if we have x raised to the m exponent times x raised to the n exponent, this is the same thing as x raised to the m plus n. In other words, when you have the product of two terms with the same base, you can add the exponents. Let's take a look at why this works. Suppose we have 2 to the third times 2 to the fourth. 2 to the third is 2 times 2 times 2. And 2 to the fourth is 2 times 2 times 2 times 2. This is the same thing as just 7 factors of 2, which is equivalent to writing 2 to the seventh. Notice that 7 is equal to 3 plus 4. That is, 2 to the third times 2 to the fourth is equal to 2 to the 3 plus 4, or 2 to the seventh. Be really careful with these. It's easy to make the mistake of writing 2 to the third times 2 to the fourth equals 2 to the 12th and accidentally multiply those exponents. But that's clearly not the same thing. Let's take a look at an example. In example 1, we're going to simplify m raised to the 9th power times m raised to the 11th. Using the product rule, we know that this is equal to m raised to the 9 plus 11. That is m to the 20th. Looking at example 2, we're again going to simplify. The good news is the product rule can be extended to more than two terms. So since we have 3 to the third times 3 squared times 3, we could simplify this as 3 to the 3 plus 2 plus 1. Remember that 3 without an exponent is really 3 to the first. So this becomes 3 to the sixth, and 3 to the sixth is 729. Let's keep moving. In example 3, we're again going to simplify. Notice that I have two terms with the same base. This time, instead of the base being a single variable, I have the base of a minus 6. The product rule still applies. This is equal to the base, a minus 6, raised to the exponent, the sum of the two exponents, 10 plus 17. So this simplifies to a minus 6 raised to an exponent of 27. In example 4, we have a few more moving parts. I have an a to the 6th, b to the 3rd, a to the 9th, and b to the 5th. Since everything here is simply being multiplied together, we can start by dropping the parentheses and writing this as a to the 6th times b to the 3rd times a to the 9th times b to the 5th. We can also write them in a different order. We could write a to the 6th times a to the 9th times b to the 3rd times b to the 5th. First, let's look at a to the 6th and a to the 9th. This simplifies to a raised to an exponent of 6 plus 9. Now looking at b to the 3rd times b to the 5th, this simplifies to b raised to the exponent of 3 plus 5. Now in our final step, we can simplify this to a raised to an exponent of 15 times b raised to the exponent of 8. Now let's take a look at another rule. According to the power rule, we know that for any base x, if we have x raised to an exponent of m, and then that's raised to an exponent of n, this is equal to x raised to the m times n. Let's take a look at why this works. Suppose we have 2 to the third raised to the fourth. That means I need 4 factors of 2 to the third. That's 2 to the third times 2 to the third times 2 to the third times 2 to the third. We know from the product rule that we can write this as 2 to the 3 plus 3 plus 3 plus 3. But notice that that's just 4 copies of 3. That's 2 to the 3 times 4, or 2 to the 12th. Let's take a look at an example. In example 5, we need to simplify a to the 9th raised to the 11th. The power rule tells us that this is a raised to the exponent of 9 times 11, or a raised to an exponent of 99. In example 6, we have a couple more things to consider. Let's first think of this as two parts. X to the 4th raised to the 6th times x to the 5th squared. X to the 4th raised to the 6th can be rewritten as x raised to the exponent of 4 times 6. X to the 5th squared can be rewritten as x to the exponent of 5 times 2. Now we have x to the 24th times x to the 10th. Now that we've used the power rule to simplify the exponents on the outside of the parentheses, we'll use the product rule to finish. This is x raised to the exponent of 24 plus 10, or simply x raised to the exponent of 34. Now let's look at another rule. The power of a product rule states that if we have a product such as x times y, and we raise that to an exponent, we could rewrite this as x raised to the exponent of n times y raised to the exponent of n. In other words, that exponent on the outside of the parentheses applies to each item in the product on the inside of the parentheses. Suppose that we had 2 times 3 raised to the 4th. That means I need 4 factors of 2 times 3. That would be 2 times 3 times 2 times 3 times 2 times 3 times 2 times 3. If we rewrite this in a different order, we have 4 factors of 2 and 4 factors of 3. That's the same thing as 2 to the 4th times 3 to the 4th, where the exponent on the outside applied to both the 2 and the 3. Let's take a look at example 7. In example 7, we have a to the 5th times b to the 3rd, all raised to the 8th power. Using the power of a product rule, we can rewrite this as a to the 5th raised to the 8th times b to the 3rd raised to the 8th. A to the 5th to the 8th is a raised to the exponent of 5 times 8. B to the 3rd raised to the 8th is b to the exponent of 3 times 8. Simplifying, this is a raised to an exponent of 40 times b raised to an exponent of 24. Let's take a look at another example. Here in example 8, there's a lot going on, but just take it one step at a time. Looking at our first set of parentheses, we know that this exponent of 3 needs to apply to the 2, the x to the 6th, and the y to the 5th. In other words, we need 2 cubed times x to the 6th cubed times y to the 5th cubed. Looking at our second set of parentheses, we know that the 2 needs to apply to the 3, the x to the 8th, and the y to the 10th. That means that we need 3 squared times x to the 8th squared times y to the 10th squared. Simplifying, we have 2 to the 3rd, or 8, times x to the 6th to the 3rd, or x to the 6 times 3, x to the 18th. Then we have y to the 5 raised to the 3rd. That's y to the exponent of 5 times 3, or y to the 15th. Next we have 3 squared, which is 9, x to the 8th squared, or x to the 16th, and y to the 10th squared, or y to the 20th. We can find the product of 8 times 9, which is 72. We can also combine our x to the 18th and our x to the 16th. Using the product rule, this is x raised to the exponent of 18 plus 16. We can also combine our y to the 15th and our y to the 20th. This becomes y raised to the exponent of 15 plus 20. Finally, at our last step, we can simplify this to 72 times x raised to the exponent of 34 times y raised to the exponent of 35. This example uses all of the properties that we've covered so far. Now let's take a look at the quotient rule. With the quotient rule, we have a fraction with x to the m in the numerator and x to the n in the denominator. The quotient rule tells us that as long as x is not 0, we can simplify this to x raised to the exponent of m minus n. That is, we'll take the difference of the exponent in the numerator and the exponent in the denominator. Consider if we had x raised to the 7th divided by x raised to the 4th. That would be 7 factors of x in the numerator and 4 factors of x in the denominator. When simplifying, notice that exactly 4 factors of x in the numerator will simplify with 4 factors of x in the denominator. This leaves us with 3 factors of x, or x to the 3rd, in the numerator. And that new exponent of 3 is the difference between our original exponents, 7 and 4. Let's take a look at example 9. In example 9, we're going to simplify, and we're going to just assume that all variables are non-zero. That way we don't have to worry about dividing by 0. Since we have n raised to the exponent of 35 divided by n raised to the 7th, we can use the quotient rule and rewrite this as n raised to the exponent of 35 minus 7. 35 minus 7 is 28, so this becomes n raised to the exponent of 28. Let's go on to example 10. Example 10 is the same as example 9, it's just written a little differently. We have x raised to the exponent of 32 divided by x raised to the 8th. The quotient rule still applies even though it's written like this. We can still simplify this to be x raised to the exponent of 32 minus 8. Since 32 minus 8 is 24, this becomes x raised to the exponent of 24. In example 11, we're going to use the quotient rule more than one time. Let's start by rewriting this just a little bit to help us see the problem more clearly. In the numerator, we have 32 times c to the 4th times d to the 12th. In the denominator, we have 16 times c times d to the 6th. Since 16 goes into 32 two times, we could simplify the 32 and the 16 to become 2 over 1, or 2. Looking at c raised to the 4th in the numerator and c raised to the 1st in the denominator, we could rewrite this as c raised to the exponent of 4 minus 1. Finally, we have a d raised to the exponent of 12 in the numerator and a d raised to the 6th in the denominator. We could rewrite this as d raised to the exponent of 12 minus 6. In our final step, we'll rewrite this as 2 times c to the 3rd times d to the 6th. Let's go on to our zero exponent rule. The zero exponent rule tells us that if we have any base x and we raise it to an exponent of 0, that's equal to 1, as long as x isn't 0 itself. Let's think about why this is true. Suppose we have x squared divided by x squared. Using the quotient rule, we know we could write this as x raised to the exponent of 2 minus 2, but that's just x to the 0. Now let's think about this another way. We have the same thing in the numerator and in the denominator, so we know that this really simplifies to 1. That is, x to the 0 is equal to 1. Let's try out some examples. In example 12, we start out with 8 raised to the exponent of 0. The zero exponent rule tells us that this is simply 1. The next one, we need to be careful. We have negative 9 to the 0. Since there's no parentheses grouping the negative with the 9, we treat this as negative 9 to the 0. 9 to the 0 is 1, so this is negative 1. If we instead had negative 9 raised to the 0 power with parentheses like this, then this would equal 1. Our last one here, we have 15 times x to the 0. X to the 0 is simply 1, so this becomes 15 times 1, or simply 15. Let's move on to our last rule. The power of a quotient rule tells us that if we have a fraction or quotient, such as x over y, raised to an exponent, like n, we can rewrite this as the numerator x raised to the exponent of n divided by the denominator y raised to the exponent of n. And this is true as long as y is not equal to 0, because we still can't divide by 0. Let's think about why this is true. Suppose we had simply x over y raised to the 3rd power. That means we need 3 factors of x over y. That's x over y times x over y times x over y. Since we have 3 fractions multiplied together, we can multiply the numerators together, and we can multiply the denominators together. 3 factors of x can be rewritten as x to the 3rd, and 3 factors of y can be written as y to the 3rd. In other words, that original exponent of 3 applied to both the numerator x and the denominator y. Let's take a look at example 13. In example 13, we're going to simplify, and we're going to assume that all variables are non-zero so that we don't have to worry about dividing by 0. First, let's look at 5 over x raised to the 4th. Using the power of a quotient rule, we know that we can rewrite this as 5 to the 4th divided by x to the 4th. 5 to the 4th is 625, so this becomes 625 divided by x to the 4th. Taking a look at this next one, we have a few things going on. First, let's start by using the power of a quotient rule and apply that exponent of 6 to both the numerator and the denominator. This becomes 10x to the 8th raised to the 6th divided by yz to the 7th raised to the 6th. Now we'll use our power of a product rule to apply that exponent of 6 to each item inside the parentheses. That means we need 10 to the 6th times x to the 8th to the 6th divided by y to the 6th times z to the 7th to the 6th. Simplifying again, we have 10 to the 6th, which is 1 million, times x to the 8th raised to the 6th, which is x raised to the exponent of 48. In the denominator, we have y to the 6th times z to the 7th raised to the 6th, or z raised to the exponent of 42. And that's as much simplifying as we can do for this one. Let's go on to our final example. In example 14, we're given a function f of x is equal to 6x squared. We're going to evaluate the function at -4 and a to the 5th. Let's start by finding f of -4. That means we want to put a -4 where the x is in the function f. So instead of 6x squared, we want 6 times -4 squared. -4 squared is -4 times -4, or positive 16. So this becomes 6 times 16, which is 96. That tells us that f of -4 is positive 96. Next, let's find f of a to the 5th. This means we want to put an a to the 5th exactly where the x is in the function. So instead of 6 times x squared, we want 6 times a to the 5th squared. Using our power rule, we can rewrite this as 6 times a to the exponent of 5 times 2, or 10. And we've now found that f of a to the 5th is 6 times a to the 10th. And that will conclude this lecture video on the properties of exponents.